Welcome back to the workshop. We want to continue taking a look at algorithms and their efficiency by looking at Horner's polynomial evaluation algorithm. So going through this algorithm, we want to actually evaluate the same polynomial that we did in our last example. So we're going to consider, I'll write it here, 2x squared plus 3x plus 4, and we're going to evaluate for x equal to 3. So for this algorithm, it takes care of things a little bit differently. And in the previous algorithm, we started at the back or the end of the polynomial and worked our way towards the beginning, or at least the beginning in how we write it down. And in this algorithm, what we do is we actually start with setting s equal to the coefficient on our very first term. So that's a little bit different. So let's go ahead and follow through what happens when we evaluate this polynomial. So step 1, we set s equal to the coefficient on our first term, which is 2. And we let k be equal to 1. So we haven't done any elementary operations yet. We haven't performed any multiplication, division, addition, subtraction, or comparisons. But as soon as we move on to step 2, we begin with a comparison, putting us into a loop. So our comparison is k less than or equal to n. Well, n is equal to 2 in this case, so is 1 less than or equal to 2? Yes. So we're going to find a new value for s, and we're going to increase the value of k. For the value of s, we're going to multiply s by x and then add the next coefficient. So we're going to do 3 times 2, so 3 times s, plus the next coefficient. So 3 times 2 plus 3. And that is equal to, so 3 times 2 is 6, 6 plus 3 is 9. And we increase the value of k to 2. All right, we get to the end while, which sends us back to the top of the loop, and we perform the comparison. So now all that we've done in the first iteration of the loop is we did a comparison, we did a multiplication, an addition, and another addition. So we did 4 operations, and it didn't depend on k at all. Right? This value depended on k, but the number of operations didn't depend on k. All right, so anyway, we completed the first iteration of the loop, and we come back to the top and we perform a comparison. Is 2 less than or equal to 2? Yes. So we perform the loop again. So step 2 again. S is equal to, we take the value of k, 9. We take the value of k, which is 9, and we multiply it by x, so x times 9 plus x times 9 plus a sub, let's see here, and minus k, so k is equal to, and minus k. 2 minus 2 is 0, right? We're adding the constant there. Excellent. So the coefficient of the next term, of course. So 3 times 9 is 27. 27 plus 4 is 31, and we set k equal to 3. All right, we get to the end while, and that brings us back to the top of the loop, and we say, is 3 less than or equal to 2? No, but we did have to perform that one additional comparison to kick us out of the loop. Now that we're out of the loop, we go all the way down to step 3. We have s is equal to 31. We have k is equal to 3, and we output p of 3 is equal to 31. Excellent. So that's the evaluation of a polynomial using Horner's polynomial evaluation algorithm. And we'll do a couple more examples of this in our next video. So let's determine the complexity of the algorithm. Okay, so I'm not going to worry about what we did here so much. I'm just going to determine the complexity like we did on the last example. And in step 1, there's no elementary operations. In step 2, there's a comparison. So let me circle our operations here, or note them. So we have a comparison, a multiplication, an addition, and one more addition. So in each loop, there are one comparison, one multiplication, and two additions. So four operations, four elementary operations in each time that we, in each iteration of the loop. The loop is, so I said completed, I think in our last example, the loop is completed n times. And what might be a little bit more appropriate language is iterated. So each time we complete the loop, it's an iteration. So the loop is iterated n times. So we go through the loop n times, right? We had to go through it. This was a polynomial degree 2, so n is equal to 2, and we had to complete it twice. So that that matches, that makes sense. So the loop is iterated n times. This gives us, oh, and then actually we should say the loop is iterated n times, and there are n plus 1 comparisons. Total. I already counted the comparisons here though, so let's actually say there is one additional comparison to kick us out of the loop. Right, so once that last comparison is made and that inequality is no longer satisfied, that kicks us out of the loop. So that one additional comparison is made. So that's 1, 2, 3, 4 elementary operations done n times. So the complexity is for n, for the 4n operations done in the loop, and then plus the one additional comparison to kick us out of the loop. And then no more elementary operations are done. So that's it, right? The calculation, the computation of the complexity of that algorithm was much easier than the last one. And that's incredible, right? They're doing the same thing. And in the case of n equal to 2, it was essentially, right, there were the same number of steps, but these steps here technically had more things going on, right? I had an exponent here, but here there's no exponent, okay, no exponent. So that's fantastic. That makes things very nice and very easy for us in the evaluation and makes the algorithm much quicker to execute when you're talking about larger polynomials, right? If you were talking about a polynomial of degree 100, which isn't necessarily crazy, we don't experience it very much, but that's not crazy at all. But you compare 4 times 100 plus 1, 401, plus 1/2 of 3 times 100 squared plus 7 times 100. Okay, huge, huge. So they're very different in terms of complexity, but they do the same job. So there are a lot of different ways to do things, right? I'm sure you've heard that in your entire life, and it's also true here where we're talking about algorithms. All right. So let's call that good for now. We want to take a look at one more algorithm in this section, and we also want to take a look at some more examples. So we'll take a look at some examples of the algorithms for evaluating polynomials, and then we'll talk about one more algorithm as well. So I'll see you back here in the workshop very soon.